reaching heights of over 100 meters. Californian sequoias tower over Earth's other estimated 60,000 tree species. Growing in the misty Sierra Nevada mountains, their massive trunks support the tallest known trees in the world. But these behemoths seem to have their limits. No sequoia on record have been able to grow taller than 130 meters. And many researchers say these trees wouldn't be that tall, even if they live for thousands of years to come. So what exactly is stopping these trees from growing taller forever? It all comes down to sap. In order for trees to grow, they need to bring sugar obtained from the photosynthesis and nutrients brought in the root system to whenever growing is happening. And just like blood corpuscles in the human body, trees are designed to circulate two kinds of sap throughout their bodies, carrying all the substance a tree's cell need to live. The first is fallen sap, containing sugar stored in the leaves during photosynthesis. Fallen sap is thick like honey and flows down the plant's phloem tissue to distribute sugar throughout the tree. But by the end of its journey, the phloem sap has thinned into a watery substance, the pooling at the base of the tree. Right beside the phloem is the tree's other tissue type, the xylem. This tissue is packed with nutrients and iron like calcium, potassium, and iron, which trees has absorbed through its roots. Here's at the tree base, there are more of these particles in one tissue than the other, so the water from the phloem sap is absorbed into the xylem to correct the balance. This process, called osmotic movement, creates nutrient-rich xylem sap, which will then travel up the trunk to spread those nutrients through the tree. But this journey faces a formidable obstacle: gravity. To accomplish this heroic act, the xylem relies on three forces: transpiration, capacity action, and root pressure. As a part of photosynthesis, leaves open and close pores called stomata. These openings allow oxygen and carbon dioxide in and out of the leaf, but they also create an opening through which water evaporates. This evaporation, called transpiration, creates negative pressure in the xylem, pulling watery xylem sap up the tree. This pull is aided by a fundamental property of water called capillary action. In other words, the action between water molecules and the acid force between water and its environment can beat out gravity. This capillary motion in full effect in cells is thinner than human hair, and where these two forces pull the sap, the osmotic movement at the tree's base creates root pressure, pushing fresh xylem sap up the trunk. Together, these forces launch sap to dizing heights, distributing nutrients, growing new leaves to photosynthesize far above the tree's roots. But despite this sophisticated science, every centimeter is a fight against gravity. As trees grow taller and taller, the supplies of this visual flux begin to dwindle. At a certain height, the tree can no longer afford lost water and that evaporates during photosynthesis. And without the photosynthesis needed to support the additional growth, the tree instead turns its resources toward the existing branches. This model, known as the hydraulic limit is currently our best explanation for why trees have limited height, even in perfect growing conditions, and using this model alongside growing rates and no need for nutrients and photosynthesis, researchers have been able to propose height limit for specific species. So far, this limit turns grow up even for the world's tallest trees still fall between 50 meters below the cap. Researchers are still investigating the possible explanation for this limit, and there may be not the one universal reason why trees stop growing, but until we learn more, the height of tree is yet another way that gravity literally shapes life on Earth.